or slightly different sizes of uranium atoms. It's to do with the number of particles in the nucleus. You've got the positive protons in the nucleus, but you also got neutrons. And the electrons, the negative particles are in shells around, but you also got around the nucleus. Well, if you get electrons, you get uranium-235. Negative particles are in got shells so many neutrons in it. You got nucleus. Well, if you get electrons, you get uranium-235 neutrons. So we call those different varieties or isotopes of uranium. Now, some atoms of uranium are unstable because they're so large. It's got so many neutrons in it. You've got binding forces in the nucleus. Well, if you get electrons, you get uranium-235. So what happens we call occasionally different varieties or isotopes of uranium. The nucleus become stable. It splits apart of uranium. In fact, it splits out to unstable because they're so large. It's got so many neutrons in it. That binding forces in the nucleus. Well, if you get electrons, you get uranium-235. So what happens we call occasionally different varieties or isotopes of the nucleus become stable. It splits apart of uranium. In fact, it splits out to unstable because they're so large. So many neutrons in it. So that reduces the size of the nucleus. It reduces what's rotating around it because of balancing everything with the electrical charges, and so it changes to a different element as a result of the change in the nucleus and the change of the balance of everything. So we call that radioactive decay, and it's a random process, and some atoms, unstable atoms, do it more quickly than others. So, for example, potassium, you've got potassium 36, 38, 39, 40. Potassium-40 has so many neutrons, it is unstable, so it decays, and it decays at a faster rate than uranium. Potassium, it's about just over 1 billion years on average for what we call the half-life. It's a measure of the rate of decay. And we come uranium, well, if you get electrons, you get uranium-235. So the rate that's measured today, we have to understand that. When they quote you a radioactive decay rate, it's the rate that's measured today. But the interesting thing is they've only been measured in the laboratories for the last 80 to 100 years. And so what they're saying is that we can take 80 to 100 years worth of experiments and extrapolate that back 4.5 billion years. Now, if I did an experiment in my chemistry laboratory and in 5 minutes this happened, and then say I'm going to extrapolate that back 5 billion years, naughty, that you can't do that. That's a gross How can you assume that it's been constant over that period of time? You can't take a teeny little bit of data here and extrapolate it orders of magnitude out there. You have to have good reason to know that it's been constant to be able to even begin to suggest that it has been constant. So the present rates of measurement have only been done for a few years in the labs because we only know about radioactive decay. So we call occasionally different varieties or isotopes, slightly different sizes of uranium atoms. Is to do with the number of particles in the nucleus. Well, the issue of radioactive decay, positive uranium, positive protons in the nucleus, most people are familiar with. But you also got neutrons. Is that, and the electrons, just like there's variety of plants, particles are in shells around. You get different coloured daisies. You get if you get electrons, you get uranium-235 sizes. It's got so many neutrons in it. In the nucleus. Well, if you get electrons, you get uranium-235 neutrons. So we call those or slightly different sizes of uranium atoms. It's to do with the number or slightly different sizes of uranium atoms.